Hello, hello. How we doing, everybody? What's going on? So I have some QR codes here. If anybody wants to follow along, we're going to be doing some pretty cool stuff here today. Before I get started here, who here is a Solidity developer? Raise your hand if you're a Solidity developer. Okay, a whole bunch of Solidity developers. Not as many as I would expect from a hackathon. What about Vyper developers? Almost no. Oh, okay, almost one. All right, excellent. Perfect. This is exactly what I wanted. Okay, cool. So today we're going to be talking about Vyper versus Solidity in terms of gas optimizations. We're going to learn a lot, and I have 19 minutes to do this talk, and I'm normally used to having 16 hours or more. So for those who do not know, my name is Patrick Collins. I'm a smart contract engineer, auditor, educator. Some of my QR codes up there. I absolutely love Web3. I live, breathe, sleep, eat smart contracts. I have done a video on this before, so if you want to grab that QR code as well, watch the video on this. You can head over there too. But today, for this presentation, we're going to just focus on a single subset. Why is Vyper oftentimes more gas efficient than Solidity? And I know, crazy, right? How could that be possible? Patrick, you've done so many videos teaching Solidity. Why are you now telling me that sometimes Vyper is better? But I'm giving the disclaimer that I still like both Vyper and Solidity. I think they're both great languages. However, as developers, we should constantly be asking, is this the best tool for what I'm doing? That's what we need to be asking all the time. Is this the best tool? How many people here ask themselves that when they're writing their code? Is this the best tool? I see 4 liars here. Excellent, excellent. All right, cool. So I'm considering myself more of a referee. I'm playing, I'm sure you do. I'm considering myself more of a referee here, but we're gonna explore why this is the case and the architectural trade-offs that go into this and get you thinking, is this the best tool? Can I make this better, right? Because as Web3, that's what we should be constantly thinking. Here is our combatants. Here are our 2 contracts that will be doing gas battle against each other. They do essentially the same thing, because at the end of the day, that's what high-level languages do. Both Solidity and Vyper compile down to EVM opcodes. They just do it in their own unique ways. So what does this code actually do? What do these 2 contracts actually do? Very basically, they have a storage variable named store number. They have an external function that allows you to set stored number and a view function to read stored number. I'm doing Solidity first. However, the Vyper code is nearly exactly identical. The syntax looks very similar. Vyper and Solidity are not so different after all. Yay, it's a great world. But they're very different under the hood. And we're going to see that in a second. So, spoiler alert, here are the results of deploying this code. Oh my goodness, Solidity is much more gas expensive than Vyper when it comes to deploying these contracts. What? How could that be? All I do is Solidity. Okay, well, cool, that's just deploying the contracts, Patrick. What about running the contracts? What about reading that storage variable? What about setting that storage variable? How's the gas look there? Well, I hate to break the news to you, Vyper is more gas efficient there as well. So for all of you who did not raise your hand and say, is this the best tool? Did not ask the question, is this the best tool I should be working with? It's time to start asking, right? But let's go deeper into this. Why is this the case? Why are we all using Solidity if Vyper is more gas effective here? What's going on? Let's go under the hood. And then, yes, I have some, when I first did this, I did some comparisons, some benchmarks to Huff, Yule, Solidity, and Yule, and some other stuff as well. That's why you see other stuff, but we will not be talking about those today. So let's explore this. Why does this bar graph exist? How is this possible? Let's talk about gas costs when it comes to contract creation. When we first deploy these 2 contracts, what is going on under the hood to make it such that Vyper is cheaper to do so? And to do that, let's do a quick refresher on EVM opcodes and a little refresher on assembly. If you're in Remix and you have your Solidity code here, when you compile it, there's this little button called bytecode. If you click that, you get this disgusting output that you see on the screen here, which is a whole bunch of opcodes for the EVM, right? It's what makes all of our smart contract stuff work. All right, who is with me so far? Raise your hand, say aye. Who is not with me? Say what? Everybody's with me? All right, great, excellent. All right, cool. And so these opcodes look something like this, right? There are just all these opcodes, and most high-level languages break down these opcodes into 3 different sections, and Solidity actually does a great job of breaking them down with this invalid opcode. You can't really see it on the screen here, but they break up these 3 sections by having this invalid code be kind of this separator. So usually the first chunk of code in your compiled contract is your contract creation code. It's the code that gets executed when you deploy your contract. And then in the middle there is what we have called the runtime code. This is actually the contract, right? This is all the code that you wrote for the contract. And then we have some metadata and some other stuff. We're going to be ignoring that for this talk here. We're just going to focus on those first top 2. So contract creation, that first lump of code, runtime code, that second lump of code, contract creation is what we're looking at right now. And if we look at these 2 pieces of code for contract creation across Vyper and Solidity for these smart contracts that we showed, we see they're very different. What's the first thing that you see here? What's the first difference you see, like right away? What do you see? Anybody? What? Size, thank you, excellent. We see Solidity has got a bunch more stuff, right? And as gas optimizers, we go, okay, well, if there's a bunch more stuff, that probably means it's doing a bunch more stuff. And to gas optimize, we want it to do less stuff. So is that what's going on? Solidity is just doing more stuff? What is this more stuff that it's doing? And if we look at Vyper here, this binary, this bytecode gets put out to these opcodes here, which is relatively simple when it comes to opcodes. There's this really important opcode in there called code copy, which basically is just saying, hey, take all that runtime code that comes after this contract creation code and stick that on the blockchain for people to do stuff with. And that's all the Vyper contract creation code is doing. It's saying, take that runtime code, slap that on the blockchain, and then we're done. So what is Solidity doing? A lot more stuff. There's a lot more opcodes there. What is Solidity doing? Well, if we look at this bottom section, ignore the top section first. That looks really similar to the Vyper stuff, right? There's that important code copy opcode. There's a whole bunch of push, dupe, other stuff. But that bottom opcode stuff is basically doing the same thing. Hey, take that runtime code, slap that onto the blockchain. But what about this top stuff? What's all this? So this lump of code right here, this is all the stuff at the top. What's it doing? Well, if we look at this bottom section, we're gonna ignore that top section for now. That's called the free memory pointer. Don't worry, we'll get back to that. But if we look at this bottom section, there's a call value, dupe, is zero, jump if, push, dupe, revert. Basically what that is doing is it's saying grab any value, any ETH that is sent with this deployed contract and check if it's 0. If it is not 0, revert. So when we're deploying our contracts, Solidity is actually checking to make sure we didn't accidentally send a whole bunch of ETH with this contract that'll be unrecoverable. Wow. Thanks, Solidity compiler. Looking out for us. 10-year-old meme hype. Let's go. So then you might ask, whoa, I thought we were comparing the same contracts here. Vyper, what the heck? Solidity is looking out for us. You're not. You're not doing the work to make sure I'm safe. To which Solidity would respond, well, if you specified a constructor and that @external def init thing, that's a constructor in Vyper. If you did that, then we would add that checker for you, right? So there's a big difference in the checker based off of whether or not you have a constructor or not in Vyper. So we'll say, okay, fine, Vyper, you get off on a technicality here. But this is one of the main things, one of the main differences between a lot of the languages in the EVM world. And they all do some type of check to make sure we don't shoot ourselves in the foot, to make sure we don't send a ton of Ethereum when we deploy our smart contract, right? We also will do checks on data lengths. We'll do checks on function selectors. Most of these high-level languages will do checks to make sure us developers don't do dumb things, because, we often do. Okay. Cool. So Solidity doing some extra checks. It looks like Vyper has those checks as well. It wasn't in that comparison, so great. Let's keep going. Let's talk about the runtime code now, because we saw where a bunch of those opcode differences has come from. It's come from those checks. We still haven't talked about that weird free memory pointer thing that I told you to ignore that we will definitely be coming back to. And we're not going to go too deep into the runtime code here because there's a lot to talk about. So this is the Vyper runtime code. This is the Solidity runtime code. It's even more. But we are going to focus on that free memory pointer because if you download the presentation, you can see these on the different opcodes here. The Solidity runtime code also has this free memory pointer stuff going on. The Vyper runtime code does not. Free memory pointer stuff, no free memory pointer stuff. Solidity has it both in contract creation and in runtime. Vyper doesn't have it anywhere. So what's going on? We found another bunch of opcodes that Solidity is using that Vyper is not. And obviously, if Solidity is doing them, it's spending gas. Who's with me so far? Say I. Who is totally lost? Say, I'm totally lost. Okay, I heard a couple mumbles. They're a little shy about being totally lost. That's okay. You can come back to this video later. I have more links to the actual code. Feel free to ask questions there. And if I do the rest of this presentation really quick, we'll have time for questions. But glad most of you are with me. Okay, great. What is this thing? And actually, most Solidity contracts will start with exactly this. Push OX80, push OX40, mstore. What does this do? Why do we have this? To understand this, we need to learn about memory and the stack. To learn what this free memory pointer is, what these opcodes are doing here. So a quick refresher, in the EVM, we have memory and we have stack, right? These two wonderful things. And when we push stuff, we push it onto the stack. And it's literally like a stack of pancakes. We push values up, 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 up. You keep going higher and higher. You push stuff on until you do some type of opcode that pulls them off. So mstore is an opcode that will pull things off the stack and will stick it into memory. And in this example, the mstore command says, okay, grab the thing that's at the top of the stack, and that's going to be the location of memory we're going to stick stuff. And then what's underneath that, we're going to stick that into that location of memory. So we took OX80, stuck that in OX40 because mstore says, hey, top of the stack, location, bottom of the stack, data. Great. And we need both a stack and a memory in the EVM, right? Stack is restricted in size. Memory is much bigger. There's a lot more memory. We don't have unlimited stack. Memory can sometimes be easier to deal with. And variables, and this is really important, variables are returned in memory, not from the stack. So anytime you return any variable in Solidity or Vyper, you need to return it in memory. But how do we know where we can put this new stuff in memory in this array, right? Let's say we have memory with a bunch of stuff in it already. If I put more stuff in memory, am I going to override what's already in there? How do we know? Well, let's see how they approach it, because this is where the gas optimization stuff comes from. Let's see how Solidity does it first. So Solidity looks like this, right? So this is memory. You can imagine this is kind of Solidity's memory here. The 0x0 and 0x20, those slots of memory are usually reserved for like hashing stuff, but the rest of it is basically free for us to use. And when we do this push mstore, we're sticking this OX80 in there. And what this is doing is it's telling Solidity, hey, there is free memory at the OX80 spot. So this position in memory, OX40 or fake index 2, is telling us where the next lump of free memory is, right? This OX40 is a special spot in memory in Solidity. And if you change, right? If you change where that spot's pointing to, you're changing where Solidity is telling you that there's free memory, right? And we could look at an example like this. So if you see uint256 2 equals 2, sorry, I know terrible naming there, we need to create this 2 variable in memory somewhere. And those are the opcodes associated with doing that. We do a push mload mstore. We load where the free memory pointer says there's free memory, and then we store our uint256.2 data where the free memory pointer says there's stuff to do, right? So if this is memory, those opcodes get run, the data gets stuck in there because that's where the free memory pointer says there's free memory, and then we update the free memory pointer to say, hey, now free memory is 1 block down, right? Make sense? Say aye if it makes sense. Excellent, okay, cool. But that's a lot of work. Every time I do anything with memory, first off, I gotta create a free memory pointer. Then every write to memory, I gotta read where free memory is first. And then every time I write to memory, I gotta update that free memory pointer. And that's a lot of work. So let's talk about how Vyper approaches this. Vyper sees all this, and my emoji got messed up there. But Vyper sees this and says, ugh, that's a lot of work. So Vyper says, let's take a different approach. Same thing. This is Vyper's memory. First, 0x0 and 0x20 are usually reserved for like hashing stuff. But this is that exact same function that we saw in Solidity, but in Vyper, it has the same uint256.2 variable that it needs to store somewhere in memory. And Vyper approaches this a little bit differently. Vyper says, wait a minute. I have exactly 2 variables that I'm going to need to store in memory. I need to store that uint256.2 variable, and then I'm going to need to store my return value in memory as well. So I have 2 things that I need to store in memory. Both of those are size 32 bytes. 2 times 32 is 64. All I need to do is just have 64 bytes of memory, and I'm good to go. I'll just have the first thing go in the 0 to 32, and the second thing go into 32 to 64. And I don't need a free memory pointer. And that's exactly what Vyper does. Vyper says, I'm just going to statically allocate this memory instead. So whenever Vyper sees this uint256.2 variable, it's just going to stick it in that OX40 every single time. It knows that a uint256 is 32 bytes. That fits exactly in our OX40 slot, and it knows that our return value is also going to be, of type uint256. So we'll stick that in the OX60, and every single time this function runs, that's exactly where I'm going to put them. I don't need a free memory pointer because I'm just going to say first variable OX40, second variable OX60. That's it. And this is where the main gas optimization differences come from, is the way that they're doing this memory allocation, this memory management. Vyper is doing memory allocation statically, whereas Solidity is doing it dynamically. Solidity has this free memory pointer that says, okay, I'm always going to keep track of where the next lump of free stuff is. And Vyper says, I'm not going to do that. I know that I'm always going to have 4 variables that I need to stick in memory, and I'm just going to stick them in the exact same 4 slots every single time. That way I don't ever have to worry about overriding. So you might be thinking, huzzah! Vyper's better. I'm just going to use Vyper. Patrick, you've convinced me. Congratulations. But remember what I said at the beginning of the presentation. Is this tool the best for the job? Constantly be asking this. And when you ask that, you should be thinking, what are the downsides of doing this? Why does Solidity not do this? What's the issue here? So let's talk about some downsides. Vyper needs to know how big everything is to put it in memory, right? If it doesn't know how big it is, it can't say, okay, uint256 goes in spot 0 if the uint256 could be a uint 2 million, because it would override, right? It needs to know exactly how big each one of these lumps of data is. So what it can't do is actually stick dynamically sized objects in memory. So for example, in Solidity, I can have a function like this. Function getArray, public returns a uint256 memory array, return my array, and that's a dynamic array that my array that it's returning could be any size. Solidity can do that. Vyper cannot do that. Vyper has what's called bounded dynamic arrays. It can't have these true kind of uncapped size of dynamic arrays. Now, the caveat to this is, in practice, this doesn't really bar Vyper from being able to do anything Solidity can do. So I put it to you all to see what you like best, to encourage you to get out of your comfort zone a little bit. try to see what you like better. And keep this in mind when you're writing Solidity code or you're writing your next lump of Vyper code. And again, the code that I did to test all these, this presentation, QR code, and then IPFS to this presentation as well. Hopefully you all enjoyed. I am 17 seconds over now. Thank you so much for listening to my talk. Hopefully you learned something. And best of luck at ETH Denver. Thank you. Any questions or no? Oh, I can't take questions? Okay. Oh, like, oh, okay.